a simple algorithm for arbitrary precision integer division. What is an integer? An integer is a number without a decimal component. That means it doesn't have any digits after the decimal place. Here are some examples of integers. Integers are a subset of real numbers, which also includes numbers that are non-integers. Non-integers do have a decimal component. These are examples of non-integers. Today, we're going to be focusing only on the integers. What do we mean by arbitrary precision? That simply means a number with any number of digits, a number of any size. To understand why we need an algorithm for arbitrary precision numbers, let's first discuss how computers store big numbers. Computers store information using tiny little switches that we call binary digits or bits. These bits can be represented by a 1 or a 0. We group bits together in groups of 8, which is 1 byte, or multiples of 8, such as 16, which are 2 bytes, 4 bytes are 32 bits, or 8 bytes are 64 bits. 1 byte is capable of storing any number from negative 127 to positive 127. That means that 1 byte can effectively store any 2-digit number from negative 99 to positive 99. Likewise, a 2-byte integer can store any 4-digit number. A 4-byte integer can store any 9-digit number, and an 8-byte integer can store any 18-digit number. These are known as data types. A 1-byte integer data type is known as a byte, char, or short integer. A 2-byte integer is known as an integer. A 4-byte integer is known as a quad int or long int. An 8-byte integer, usually available only on 64-bit systems, is called an ultra-long int or a ulong. If we compare our 8-byte 18-digit integer to our original number from the example, we can see that it simply doesn't have enough digits to represent that number. Data types with more bytes have increasing precision. The highest number that a data type can represent is called its precision limit. After that, the remaining digits are overflow and are simply removed from the resulting integer. Some might ask at this point, why not use floating point data types? Floating point data types use exponential notation to represent very large numbers and can include decimal values. The problem with floating point data types is they too have a precision limit. With a floating point data type, the precision limit results in digits to the right being truncated. Again, arbitrary precision simply means a number of any size. And as we've seen, there are challenges representing an arbitrary number using the computer's built-in data types. Why do we need a simple algorithm? For built-in data types, the computer is able to perform simple math functions such as addition, subtraction, multiplication, and division. For our arbitrary precision data type, we have to write an algorithm or a set of steps to tell the computer how to perform these functions. For addition, the steps are very simple. We learned this in elementary school. We take the first 2 digits on the right and add them together. If the result is greater than 10, we carry the 1. We then add the carry into the next set of digits. We repeat this process until we have our answer. Subtraction is simply a special case of addition where the second number is negative. Again, we can perform the same set of steps but simply use a negative carry. For multiplication, again, we have a very simple set of steps that we can follow. We multiply every digit in the second number by every digit in the first number. At each step, we get an intermediate product, which we then total to find our final answer. For division, surprisingly, there is no simple algorithm. Some algorithms start with the simple step, make a guess. Guessing is just simply not something computers do well. Other algorithms require the use of logarithms. Logarithms suffer from the same precision limits and are difficult to compute. Let's look at what division really is. What is division? Division is when you take a number called the numerator and you divide it by the denominator. The denominator represents a bucket of a particular size. So, for example, if we take 20 apples as our numerator and we divide it by a bucket that can hold 5 apples, the answer to our division problem is how many buckets do we need in order to hold 20 apples? The answer is 4, which is also our quotient. If we had some apples left over, this would be our remainder. We can write this as a formula. The numerator over the denominator is equal to the quotient plus the remainder, which is really simply a fraction of the denominator. We can then rewrite this as the following formula. The numerator is equal to the quotient times the denominator plus the remainder. We're going to be focusing on this format of the formula. Let's look at the manual process that we use for division. I'm sure we're all familiar with the square bracket from elementary school when we learned how to divide. The first step is to put the numerator inside the box. We then put the denominator outside the box. We take a guess about how many times the denominator can go into the equivalent number of digits in the numerator. In this case, we're going to guess 1 times. We take our guess, multiply by the denominator, then subtract those digits from the numerator, and we get our result. Since our result is less than the denominator, we guessed correctly. We then carry down our next digit. We have to take another guess, but now we have a problem. We have 56,789. We have to guess how many times that goes into 432,109. Is it 7 times or 8 times? We're not sure. That's the problem with this process. It's very difficult for a computer to follow this process. So let's look at an algorithm instead. The first step is to cancel out all of our insignificant digits. This leaves us with 1 digit in the denominator. This results in a very simple math problem that you could almost do in your head. Obviously, we can't simply eliminate all the other digits. They are part of the solution to the problem. Let's multiply our quotient candidate times our denominator to find out how far off we are. We take the result and subtract it from our numerator, and we get the result. This result also happens to be our remainder. If we look at our division equation, we can rearrange it in terms of the remainder. We can see that our math follows this equation. This is an iterative process. So the first thing we do is store our quotient candidate. We also need to store our original numerator because we're going to have to keep comparing to that value. We then substitute our remainder for the numerator and repeat the process. We cancel out all but the first digit of the denominator. We perform our division again. This time the answer that we get isn't a quotient by itself, but has to be added to our previous candidate. This results in a new quotient candidate that we multiply by the denominator, and then we subtract that from the numerator in order to find out how far off our remainder is. Notice that this time we get a negative remainder. That's okay because that just means our quotient candidate is too high. On the next iteration, we'll end up subtracting from our quotient candidate in order to get a smaller candidate. Again, we repeat the process. We cancel all but the first digit of the denominator. We divide. Now we have a negative component to add to our quotient candidate. This results in a slightly lower quotient candidate that we substitute back into our algorithm. We multiply by the denominator, we subtract from our numerator, and we come up with a new remainder. We substitute that back into our algorithm and adopt our new quotient candidate. Again, we repeat the process. Cancel, divide, add our new quotient component, substitute our new quotient candidate, subtract from our numerator, and there's our remainder. Again, we have a negative remainder. One more time, we substitute. We divide. Add our quotient component to our quotient candidate. We have a new quotient candidate that we then multiply. We subtract that from our numerator. And we have a new remainder. This time, something strange has happened. Our remainder is less than our denominator. What this really means is that our previous quotient candidate is the final answer, and our remainder is truly the remainder of our division problem. We can easily check this. If we take our denominator, multiply by our quotient, and then add our remainder, we get our original numerator. Let's look at the steps involved in manual division and why it's difficult to turn this into a computer algorithm. If we let L be the number of digits in our denominator D, then L is equal to 5. If we let R, our result, be a number formed by the L leftmost digits of n, that results in the first 5 digits of n, our numerator. We then take a guess at a single digit that when multiplied by our denominator is then subtracted from our result. If we guess too high, we have to go back and subtract 1 and guess again. If we guess too low, then we have to add 1 and go back and guess again. Then, in order to bring down the next digit, we multiply our temporary result, R, by 10. Once we have the right guess, we subtract. We then grab the next digit of n by adding 1 to L, which was our length, which is now 6, and grabbing the 6th digit of our numerator. We add that digit to our previous result, and then repeat the process until we have an answer. Let's look at some of the complexities. The first complexity is that we have to basically treat n as a string instead of a number, or we have to perform some very complicated math in order to figure out which digits we're using. We have to take a guess. Computers don't really guess very well. In order to facilitate that guess, we have a feedback process. And the complexity comes into play where your guess could be off by as much as 10 or 20. Repeating the guessing process is iterative. Again, we extract a digit of n. In order to do that, we treat n as if it were a string, not really a number. Finally, we loop back. But even with this, we have a problem. We're not quite sure where to stop performing our algorithm. Where do we exit? How do we know when we've finished the problem? So let's compare this to our simple algorithm. The first step is to create m, which is the magnitude minus 1 of our denominator. If our denominator is 1, 2, 3, 4, 5, our total length would be 5, and m would be 4. This is the only tricky bit where it's faster to use strings. A is going to be our quick divisor. This is our shortcut for performing simple division. A is basically the first digit of D followed by a string of zeros. So if D is 1, 2, 3, 4, 5, then A is equal to a 1, our first digit of D, followed by all zeros, which is 1, 0, 0, 0, 0. We set an initial value for our quotient candidate. We divide the numerator by our quick divisor. Following our formula for the remainder, we come up with our first remainder. The next step is to substitute that remainder back into our algorithm. Our new quotient candidate is equal to our previous quotient candidate plus the next little bit that we get by dividing our previous remainder by our quick divisor. This step wasn't mentioned previously, but it dampens oscillation and helps us find the right answer more quickly. We take our new and old quotient candidates and divide by 2. If the absolute value of r is greater than or equal to d, meaning our remainder is greater in magnitude than our denominator, we go back to the beginning of the loop. If not, then we just simply continue to the next step. In most cases, r contains a junk value. We have to do one more calculation for r in order to find the right value. In some cases, r can be negative. What this indicates is that q is off by 1. If r is greater than or equal to 0, then we're done. If not, then we have to perform some steps. We adjust q by subtracting 1. But remember that r is just a fraction of d. In order to make r positive, we add d. And that's it. Q is equal to our quotient, r is equal to our remainder, and we can check it using our simple division formula. Let's compare these algorithms. The simple algorithm is a set of steps that you can easily interpret into computer code. The manual division process includes steps that are complex and require interpretation or guesswork. Here's an example of an implementation of this algorithm being run in order to divide a 54-digit number by a 12-digit number. This was calculated in 128 steps. For your entertainment, I present a 79-digit number divided by a 31-digit number requiring only 147 steps. For more information, go to justinpartech.com. The full URL for this article has been provided. You can also search for integer division on justinpartech.com. I created this presentation using LibreOffice, which is an excellent open source alternative to other Office suites. You can obtain LibreOffice at libreoffice.org. Thank you for watching.